Hi there. Somewhat reluctantly, I spent a lot more than I normally would on an eBay purchase, namely this Data Precision 8200 DC calibrator described as having problems. This is the first power up, apologies for the bad focus. Well, no magic smoke appears, so far so good. But -10 something volts when it's supposed to be 0 is not encouraging, and it does not change, and none of the digits change when I turn the knobs. Only turning it to millivolts does something in that the voltage is nearly 0. And milliamp mode also doesn't look healthy. Now we come to a problem with this video. Pretty concerned, I dived right into troubleshooting and forgot to keep a video record, so unfortunately I can only explain but not show. Part of the problem was my ignorance on how this thing operates. If the left control is set to 0, the dial knobs are simply ignored and the display always shows 0. This is by design and not a fault. The same with the millivolt setting, making the output go to 0. That's because the unit is designed to output millivolts at the rear and not the front terminals. The problem with the -10 volts turned out to be caused by tarnished relay contacts, which contact cleaning fixed. So rather than repair, this video is more about how this thing works. Opening the unit by taking the lid off, and it shows a well-organized construction. The left PCB is the digital board responsible for driving the display and scanning the control dials. On the right, under a shield, we have the analog part that produces the selected voltages or currents. It looks a bit strange because of all the residue of cal stickers covering the holes with trim pots below. The rear has a cardboard shield over an enormous mains transformer and the GPIB interface board for the remote control. With the cardboard removed, this is the transformer. I think it's already prepared for powering the 1000 volt options. These tabs are on the bottom, but of course unused in mine. Next to the transformer is the GPIB or IEEE 488 interface option. It has its own processor and allows full remote control of the 8200. The front has a vertical PCB with all the 7 segment displays and a horizontal PCB where the controls are mounted. The really expensive stuff is of course under the metal shield. To better understand what's going on here, it helps to first look at the principles of operation. Starting with the specs for the Data Precision 8200. It shows here that it has 3 voltage ranges, 100 millivolts, 10 volts and 100 volts. Interestingly, the full range values are rather specific numbers like 10.48575 volts instead of just 10 volts. We'll cover why in a moment. I already mentioned that there is an option to add a 1000 volt range, but mine doesn't have it. There's a guy in the States selling spare 8200 parts and he wants about $900 for the 1000 volt options plus shipping. That's way too steep for me, so 100 volts it is. The accuracy is stated in ppm, which stands for parts per million. To convert this into the more familiar percent, you have to divide by 10,000. So for the 10 volt range, 10 ppm is 0.001%, which is slightly better than both of my 6.5 digit meters. There's one current range of 100 milliamps, which is about as accurate as my Agilent 3441A in that range. The block diagram from the service manual is rather overloaded and confusing, but there is just one thing I want to point out. The digital part sends the desired output as a 20-bit plus sign value to the analog part. This happens through opto-isolators, so the analog output is floating. To save in optocouplers, the data transfer is done serial and hence it needs only 3, one each for data, clock and strobe. With the clock and data lines, the desired bit pattern is clocked into a shift register in the analog part and the strobe tells when the transfer is complete. The digital data pattern then passes through a digital to analog converter or DAC and finally through an output stage. This is obvious enough, but the interesting thing is how Data Precision designed a high precision 21-bit DAC in the early 1980s. As a start, the DAC really is 21 bits with a little caveat which I will explain in a moment. The 21 bits here are split into 7 groups of 3, which I try to indicate with the coloring. Now 21 bits gives you a maximum value of just above 2 million when they are all set. We know the output is 10.485 something, which means the least significant bit is equivalent to 5 microvolts. If we list the possible digital values that could be set and multiply by 5 microvolts, we get the expected output voltage of the DAC. The caveat I mentioned earlier is that the lowest bit cannot be set by the user. It is always 0 as long as the output is set to produce positive voltages. The point of all this is that from a user perspective, the DAC is back to 20 bits. This means of the output table on the right, only every second entry can appear, like 0, 10, 20, 30 microvolts and so on. This is why the spec states the resolution of the 10 volt range as 10 microvolts, even though internally the DAC is designed for 5 microvolts. So far, so confusing maybe, but it gets more interesting. Instead of making one DAC for 21 bits, the 8200 actually implements 7 DACs of 3 bits each. This starts by making the reference voltage 10.485755 and dividing it into 8 equal parts and naming each new voltage V7 to V0. V7 happens to be the original 10.85 and V0 is of course 0. The values in between are calculated as shown here. The circuit shown is much simplified. In reality, the voltage reference provided from an oven-compensated reference zener LM299 and a laser-trimmed op-amp in form of the AD517. The division into 8 voltages is done using fixed resistors and 20-turn trim ports for each, and the manual warns against attempting to adjust these without having high-class measuring equipment. Each of the 7 3-bit mini DACs is built like this. An analog multiplexer receives the same 8 reference voltages on the analog inputs. The 3 digital inputs are connected to the appropriate 3 bits of the 21-bit words in the shift register, starting with bits 19 to 17 for the highest mini DAC using Z7. The next one, Z8, deals with bits 16 to 14 and so on. The bit pattern selects which of the reference voltages is passed to the mini DAC's output op-amp buffer. If the 3 bits are set to all 0, it's V0. If the pattern is 001, it's V1, and so on until all 1s for V7. The outputs of all mini DACs are combined, but the contribution of each needs to be scaled in accordance to its position in the total 20-bit word. This is indicated with a weighting resistance RW for each. The mini DAC dealing with the most significant bits, which is Z7 in the 8200, needs the lowest weighting resistance, and the one for the lowest significant bits, Z13, needs the highest. There is a significant problem with this whole thing. The weighting resistance increases as a power of 8. In the 8200, the resistance for Z7 is 1K. In this scheme, the precision resistor needed for Z13 would be a ridiculous 262.144 megaohm. What data precision did is to insert R44, so the contribution of Z10 to Z13 is not direct but through R44, which is a precision resistor of 447.23K, 0.02%. That way, the RW values for the 4 mini DACs can be picked again to start at 1K, then 8K, 64 and so on. This whole thing is basically a balance between precision and cost. With this method, the effects of the op-amp offsets and resistor accuracy and temperature drift for the mini DACs Z10 to Z13 do not contribute a lot to the overall, and therefore the op-amps are normal TL062, the resistors fixed 0.1% types with 15 ppm temperature coefficient. Still good, but by no means what is used up there for the most significant mini DACs in terms of op-amps, resistor specs and other components. Z19 is the op-amp that buffers the combined output of all mini DACs and is therefore providing the resulting total voltage between 0 and 10.48575 volts. Positive or negative voltages are realized by these MOSFETs, which reverse the way the whole DAC, including the 8 reference voltages, appear between the low terminal and the input to Z19. For positive values, V0, which is of course 0, is connected to the low terminal, and Z19 sees the output of the DAC as positive voltage. For negative voltages, V7 is connected to the low terminal, and to get a 0 output, the DAC needs to be programmed with a maximum of all bits set to 1. Putting all bits to 0 produces minus V7 at the DAC output. Hence, for negative values, the LSB is always set to 1 and the processor programs the DAC with the ones complement of the selected value. Finally, down here we have 4 relay coils. Relays K1 to K3 select the range 10 milliamps, 100 volts and 100 millivolts. I think K4 is for the 1000 volt option. Anyway, it's not on my unit. The 10 volt range is the default where you get the direct output of the DAC. If 100 volts is selected, the signal is routed through the 100 volt amplifier up here. If 100 millivolts is selected, the 0 to 10 volt signal is routed to a simple divide by 10 voltage divider on the connector of the rear panel. If you want more information and advice on repairing and calibrating, I recommend these sites here. The links are also in the description of this video. Especially the last one is a brilliant paper which helps me a lot in understanding the way the 8200 works, and it has some valuable hints on making it more accurate by upgrading some components, which I'm considering. But enough theory, let's get a bit more practical. The date codes of the chips in my unit were mostly from the 1995, making my unit 30 years old. Since there are relatively few electrolytic and tantalum caps, I decided to replace all of them. There are also a few modifications I want to do. The Torx screws holding the lower shield of the analog board presents a little bit of a problem. I can loosen them easy enough, but then they just spin. It turns out that they screw into the standoffs holding the upper shield. So to get the screws out, I have to either prevent the standoffs from spinning or hold the screws and spin the standoff instead. Either way, that is easily accomplished. On my unit, the plastic on the binding post for the guard terminal is missing. I decided to replace it with a new binding post after desoldering the wires attached to it. Unfortunately, I forgot to film the replacement and resoldering. Well, at least you can see the new guard binding post here. I mentioned already that the millivolt output is only on the rear, which is rather inconvenient if the unit is in a stack of other devices. I decided to add a millivolt output on the front, for which I'm drilling a hole here. It is for a 3.5mm stereo jack, allowing for guard, low and high. I can either use an adapter like this or a shielded cable with banana plugs on the end. While we are on the subject, this is the rear millivolt output. The two precision resistors are the voltage divider converting the 10 volt range to millivolts. The 8200 uses an obsolete microphone connector for which the mating plugs are very hard to find, so owners are replacing it with an XLR microphone connector. I decided to do the same and ordered a good quality connector and mating plug, both with gold-plated contacts. The XLR connector is slightly larger than the old one and needs additional 2 holes for mounting screws. This type of mechanical work is done best when the PCBs are removed. After working on this for a bit and cleaning up, the new connector fits. And with the recapped analog board back installed, it can be rewired. Similar to the one for the front socket, I made a cable for it with banana plugs on the end. It's probably not a good idea to leave either permanently plugged in. While the millivolt output is only active when the millivolts are selected, unshrouded banana plugs can easily touch each other or some other grounded piece of metal, and I have not found any hint whether the millivolt or any other output survives short circuits. Here's a few of the relays that gave me a lot of trouble. Unfortunately, the relays are obsolete, so if the trouble persists, the only way forward is designing an adapter board that converts the unusual pinouts of the obsolete relays into something that's available now. The large black boxy thing is a single precision resistor R65 of 89.98K, which is part of the 100 volt amplifier circuits. The black round thing next to R65 is a protection shield for Z19, the op-amp combining and buffering the 8-octal mini DAC outputs. The other interesting thing is the smaller black round object with 2 red wires coming out of it. This is a precision 10 ohm shunt measuring the current in the milliamp range using 4-wire mode. Basically, the circuit produces current until the voltage drop over the 10 ohm shunt matches the voltage from the DAC. In milliamp mode, the processor limits the maximum value you can enter, so the highest stack output is 1 volt, which translates to 100 milliamps. This here is the LM299 voltage reference at the core of the whole thing. Here are all the adjustments. The manual classifies them into 2 categories. The ones I put in the white dotted box you better not touch unless you have access to accurate calibration equipment exceeding 6.5 digits in accuracy. This leaves just 3 that can be field calibrated, as the manual says. Even those need very accurate equipment, which is why I choose not to touch them until after I put my Agilent 34401 again to an accredited cal lab early next year. Putting the machine all back together, here's my Brymen 869S connected to the front output while the 8200 is in the 10 volt range. The Brymen is nearly 6 years old now, but still remarkably accurate without recalibrations. This allows me to demonstrate the rollover. While the 8200 has a knob for every digit like other calibrators, the microprocessor implements a smart and convenient rollover that many other calibrators do not have. On the flip side, other calibrators may not reset the dialed-in number when switching polarity like the 8200 does. In fact, I often simply reverse the banana plugs, which is faster than re-entering the desired number, especially if you have to do the polarity switching a number of times. Moving on to the 100 volt range, and it works fine. I have to say it's quite convenient compared to the convoluted way I was testing accuracy in the 100 volt range before. The range control knob actually goes all the way to 1000 volt, so what happens when I select it even though the 1000 option is not installed? A nice error message is displayed and 0 volts are sent out. Testing the millivolts from the rear output now, and the BM869S is actually still in its volt range, which is of course not ideal. I switched it to millivolts but totally forgot to enable the high-res mode. Well, here it is, and as you can see the BM869S does not really measure 100 nanovolt steps, but it does show 1 microvolt with 2 or 3 counts offset. With these low voltages, one has to constantly battle with thermal EMF voltages caused by dissimilar metals in the connections of the leads, the sockets and so on. Now for the milliamp range. First 10 milliamps. On milliamps, the accuracy of the BM869S is about 10 times less than for volts, so I'm not surprised of the reading. Notice that the 8200 ignores my attempts to set the highest digit. As I mentioned, this is because the current output is limited to 100 milliamp max. By using the 10 milliamp digit, I can of course dial that one up all the way to 100 milliamps. Let's try a low current, for example 0.1 milliamp, and that works fine. 10 microamps is similar, and we are probably again in the range of currents caused by thermal EMF. So let's select 0 milliamp output and rel the meter and see if that helps. Selecting 1 microamp, and yes, that looks very close. 2, 3, 4 and so on. All the way to 10 microamps, no problem. My 8200 has the IEEE 488 interface option, and the manual contains this selection here explaining how to remote control the unit. I have to say it leaves a lot unsaid, and it took a bit of experimenting to get this working. I'm using my Arduino based GPIB to USB interface I built some time ago. I set the 8200 to address 4, so this is the first thing that needs to be set. I should also explain that using putty to command this is inconvenient, as there is no way to fix typos. Once you press a key, it's sent and there's no editing. So let's say you want to set it to +1 volt in the 10 volt range. I need to type V for volt, 1 for 10 volt range, plus for plus, and then 01 followed by 6 zeros. The 8200 is very picky and wants the number of digits to be exactly right, so you have to fill with zeros. Setting it to -5 volts is done like this. Here I made a mistake and editing is not supported. The 8200 ignores the command. Let's try that again. There you go. Setting it to 100 volts like this. After another typo, this is how to set 1 millivolt and 100 millivolts. And finally setting it to 1 milliamp like this. Needless to say, once I had figured out the syntax, I wrote a little Python program that allowed me to control the 8200 much more comfortably. Okay, that's all I have for now on my data precision 8200. As I said, I will attempt tweaking the calibration once I'm confident that my Agilent 34401 is up to it. For now, it's pretty good already, and I'm certainly able to check the DC volts and milliamp ranges on meters with 5.5 or less digits. If you like my videos, don't forget to like and subscribe and help growing this channel. And consider becoming a Patreon, the link is in the description. Thanks for watching.